On the code word stabilizer formalism. So we're quite familiar with stabilizer codes, this quantum analog to additive codes. But there also exists non-additive codes that have better parameters than some stabilizer codes. So while stabilizer codes provide a systematic way to construct quantum codes, the existence of these useful non-additive codes created some kind of desire or like an impulse to search for ways to construct codes that encompass both additive and non-additive codes. So code word stabilizer codes, or CWS codes, provide a way that this can be done, that we can construct such codes. So I think it's easiest to see what they're like by just sort of jumping into them. So a code word, a CWS code, is defined by a stabilizer state. So some S will give you a single state, and then a series of word operators, which map this state to our different basis states. So just to highlight the difference with a stabilizer code, here the stabilizer would map us down to k elements. With the CWS code, our stabilizer maps to a single ket, and then it's k word operators that map to the different states. So what's the use of this type of structure? Well, I think to get the use of this structure, first have to look at graph states. So a graph state is a quantum state that can be represented by a graph. So if you don't know, a graph is an ordered pair of vertices, or can be given as an ordered pair of vertices and edges. And in the graph, we'll have different elements represented by vertices, and they're connected by edges that depict some kind of relationship between those vertices. So the way we use graphs for graph states is that each vertex represents a single qubit in the plus state, and edges between these are given represented by control z's. So for example, let's take a very simple graph. So the graph state for this graph would be controlled z between the first and second qubit and 2 qubits. So that is a state that can be written as a graph state. So these graph states also have stabilizers that stabilize them. And the use of using this format is the convenient form of these stabilizers. So let's go. Whoa. So they're stabilized by a set, or a group, sorry, in this form. So each generator has a single x operator, and then a series of i's and z's. So this would be for a equals 1, for a equals 2, it's in the second location, a equals 3, etc. And so to convince yourself that this does stabilize, clearly by its definition, there's no way we could have negative identity. There isn't a negative phase, and everything contains at least one x. And as well, to see that they're a group, if you pick any two of these, say, to be general, A and A prime. So at location XA, you have an X, and A prime, you have an X. If they aren't neighbors, they'll have an identity in each other's location, because there isn't an edge connecting them. And if they are neighbors, there'll be a Z connecting them in each location. So then the two negative phases come out and they do commute. So what's interesting about this form? So the theorem, or sort of the first major punchline here, is that if you have some NK CWS code with word operators and stabilizer S. This is locally Clifford equivalent to a CWS code where the word operators consist only of Z's, and the stabilizer is the stabilizer for a graph state. So originally, these word operators didn't have any restriction on them. That mapping between S to these different basis states could have been anything. It could be some combination of X's, Z's, Y's, and I's. That's okay. But they're locally Clifford equivalent to this form.
Sorry, yeah. So you said that they didn't have any restrictions. They could be tensor products of X, Y, Z, and I.
Yeah, and qubit.
That they have to be polys.
They have to be polys, yes. Sorry. Thank you. So quick proof of this. So the first part of this proof, like the mapping between this S to here, isn't given in this paper. This is a result that has already existed, that a stabilizer state is locally Clifford equivalent to a graph state. What is new is this part of it, though. So whatever Clifford gate does this mapping, call that C, its action on our word operators is as such. It acts under conjugation. And so these new word operators could, in theory, still have X's in them. But if we look at what happens, let's say we pick one that has an X in a few locations and apply it to one of our new states. So I'll pick something, say like that. Well, what we can do is we know that this is stabilized by an element that has an X on one location and Z everywhere else. So we choose the one that has an X on the first location and on the fourth location. Okay? This is equivalent to some X on the first location and then some combination of Z's. I'll just put, that's just there to symbolize some string of Z's. And then same here. And that B represents some string of B's. Well, if we multiply this through, the X's will cancel out. And we're left with something of this form. So we started with this operator acting on this state, and in the end, we're given this operator acting on this state. So we can actually choose our word operators in such a way that they only consist of some combination of Z's. So now we can give a code word stabilized code with a single graph state and a single classical code. And actually, we'll build to that. So I guess the next major punchline here, using the same logic, is that any single qubit error acting on one of our CWS states in standard form is equivalent up to phase by a potentially multi-qubit Z error. So how do we show that? I'll go over here. There's definitely an art to choosing the order of boards. An art I do not know yet. So let's choose some error. Again, we're thinking of single qubit errors. So if it's just a Z, we're fine. Nothing happens. That's trivially true. Let's pick something that's not a Z, though. Just some error. So it's an X or it's a Y. So if we consider the effect of this state on one of our new states in standard form? Well, going back to our definition of these, we pull out the operator and leave this as just the state stabilized by the stabilizer in standard form. These, and then we pull out the stabilizer element that has the x at the I location. These are both polys. So they're either going to commute or anti-commute. And this we can just revert back to the definition we had for it. Okay. So we haven't done anything, tricky yet. Just going through the math, we've pulled out this stabilizer element that's at the location that this error occurs. So if we write that out, this is some x at that location and then some string of z's. And so now if we consider the different possible errors, if ei equals xi, xi, and we're left with just z errors. If ei equals yi up to a phase, we're then left with, again, the x's will cancel out. And we're left with that. So all errors end up being mapped to just z errors. On the graph, this actually has a really nice physical interpretation. So if you imagine you have your graph state, and some error comes along, if you take your graph state, you're not changing anything by pulling out the stabilizer that corresponds with an x in that location. So the x is here. It has edges connected to this qubit and this qubit. So z's come there. Now this is x acting on this x, cancels out, and we're left with this state. If it was a y error, the same thing would occur, but there'd be a z left in its spot. So that's sort of the graphical interpretation of that. So we can see now that we can define our errors simply by a classical bit string. So there's some mapping that exists. Where we have a 0 if there's no z in that location, and a 1 if there is a z in that location. Mapping on z errors, that's trivial. It just is v. Acting on x errors, well, for each x at the location of the u, there'll be a string of z's connected to it. You then sum up all those different z's, because two z's will cancel out, so it's a modular 2 addition. That makes sense. So for each of these u's, we take the string associated with the z of that generator. So then the total error mapping for some general error looks like that. So let me just check the time. Okay. So I won't go into the error correction conditions, but I will just sort of mention the punchline. And that is that in a standard form, if with the classical errors that are given and with the graph state we have, if the code can correct the classical code given by the error set, if this can be corrected by this classical code, and one of these two other conditions are true, what am I doing? Then our CWS code can correct that set of errors, or detect that set of errors. So a claim that was made earlier that I started with was that all stabilizer codes are a CWS code. And I just want to show how that's true. So a stabilizer is given as so with n minus k elements, and it has the logical operators of this form. So these stabilizers will define a set, say something that looks like this, some logical states, etc. The code word stabilize, the CWS code that corresponds to this stabilizer code is one where the generator, there's a generating stabilizer for the stabilizer, takes the same stabilizer elements, but it adds all these logical Z operators. Of these, so the first few elements narrows down to this again, but to also be stabilized by all the logical Z operators, the only state that does that is the all zeros. The word operators are then defined to be our logical x's. Each of these different logical x's will map these to one of these different states, and then all possible combinations will map these to all possible states. So with the stabilizer state, in this form, we're giving k elements right away. Instead, with this, we're given one element, and then k operators that map us back to that same set. So I'm sort of butchering the use of sets sometimes here. So I want to give one example of it. So a code that we all know and love is the 5-qubit code with cyclic permutations. And it has logical X, logical Z. In the same way, this defines two states. If we now go to the CWS framework and we include this Z operator, we only have this state, which is stabilized by the CWS code. And then we have two word operators, the logical X and the logical X with itself, which is just the identity. So what's interesting is that the stabilizers for this are locally Clifford equivalent to a set of stabilizers, or sorry, a group that looks like this with cyclic permutations. And in this form, it's written as a graph state stabilizer. So we can write this as a graph. So if you think of each of these cyclic rotations, the location of the vertice has an edge to each of its neighbors. That's true for the five different elements. And so we get this ring. So we have our graph state. Where do we get the classical code from? One way to go about it is to look at the Clifford operation that did this mapping and apply that to our original word operators. A slightly easier way, at least I think is an easier way, is to look at the bit string that each of these errors represent. So Z1 error is like so, Z2 error is like so, etc. X1 error, X1 error is like so. Sorry. I'm running out of space. So with the Z shifted to right before and after it, and the Y is the combination of these two. If you look at this as our classical code, we need two code words such that no two of these errors map one to the other. So we can choose our classical code words to be that. So this classical code, along with that graph state, in the standard form, gives us the 5-qubit code. These ring codes, oh sorry, I should explain what that is. So this takes the shape of a ring, so we call it a ring code. are an interesting family of such CWS codes that have been explored. That there's examples that have been done, non-additive codes that were found that had better parameters, like a 9-qubit one that fits this ring model. And it's easy to extrapolate from there to do other larger qubit models. And essentially how these searches work is you pick your graph state, so you can play with different shapes. There's these double rings that are interesting, single rings. There's many shapes you can think of. And then you do a search for the classical code words that correct when you've defined your error set like this. And there's algorithms that exist to search for such examples of CWS codes. So I don't get a chance to get into it now, but if you're interested, these have also been studied for higher dimensions, and search algorithms have also been found for finding such codes, both of which I look at in my paper. So if anyone wants, just let me know and I can send you my paper. But I think that's all I have, so thank you for listening. Yeah?
Okay, I have a question. Does the fact that the 5-qubit code is cyclical have anything to do with the fact that you make a ring in the graph state?
Well, the fact that these are cyclical, yes. For the, like, in general, the ring codes, oh, it doesn't move. In general, the ring codes will have to look like this, right? And the identity elsewhere. So this could be locally Clifford equivalent to something that looks like this, but it can also be locally Clifford equivalent to something that doesn't necessarily look like that. So my best answer is maybe, but what's more important is that when they're in standard form, they look like that and are cyclical.
So when you're saying that the stabilizer codes or CWS codes, you got this stabilizer state here, but that's not necessarily a graph state that you've written down.
This is not necessarily.
Well, I'm putting to the next one.
This is not necessarily a graph state. Right, but this is locally Clifford equivalent to a graph state. Did that answer it? No.
Yes.
Oh, okay.
I would go even further and say that, in fact, any stabilizer state is locally equivalent to a graph state.
Yeah.
So
yeah.
I'm not familiar with this formalism, but is there any know about like how to decode error correct?
There was a paper on decoding that I didn't get to. Error correction, yes. There's an error correction procedure that goes through, that I go through in my paper. It was just sort of long to like fit it in. Like it sort of was proof heavy, but it's.
Does it utilize error correction with the base classical codes or?
So the way that it goes about error correction is that it looks at the classical code and it just searches for, so because we're only considering one type of error, not X's and Z errors, it essentially reduces the problem to searching for a classical code, given the restrictions of a graph state. So once you pick your graph state, you're just searching for classical codes. And so if they meet the classical error correction conditions, then and this other, there's like an OR case, I forget which board I put it on. And that OR case just deals with the case of degeneracy. So if you can deal with that degeneracy condition, any classical code word that, or any classical code that you can find that corrects a certain set of errors, given your graph, can then be put into a CWS code to give you a quantum error correcting code.
Okay, so we better move on to the next one. We have a bunch more to do. So thanks.
Yeah.
So I'm Lane, and my talk is on quantum turbo codes. But for the most part, I'll be talking about quantum convolutional codes because they're directly implemented for quantum turbo codes, and I'm going to prove like an important limitation on quantum convolutional codes. So first thing first, why do we care about different encoding schemes? Well, we want to be able to transmit quantum information with pretty high security against errors and whatever not. But also, in my opinion, more importantly, it's mathematically interesting to study. So first, I'm going to talk a little bit about some notation that I use. And then secondly, I'll talk about quantum convolutional codes as well as like definitions related to it. Then I'll move to the limitation that we have on them. Then talk about quantum turbo codes at last. And if time allows, talk a little bit about some generalization that I worked on for it. So we're all familiar with the polys I, X, Y, and Z, and I'm going to just ignore phases everywhere except where they particularly matter. So the first thing that I want to talk about is, so P1 is a single poly, so it's I, X, Y, Z. Let me know if you can't read something that I write. But anyway, so P1 is this, so then a n-qubit poly is just defined as the tensor product of n polys on one qubit. And because we're ignoring phase, it looks like x times z is like z times x. You know, they're basically the same thing. And so this incites us to create an isomorphism between the polys and two n-bit numbers. So we briefly covered this in class. So I'm going to call it phi, and it basically maps Pn into like a direct sum of 5 representations of each of the 1-qubit polys, where we have phi 1 identity is 0, 0. One moment. 1, 0, 5, y, 1, 1, and phi z is 0, 1. I'll be using this at times to make some things a little easier. Okay, so, and then beyond that, we also are all familiar with stabilizer formalism and stabilizer algebras formed by taking compositions of the generators that we have. So I'm going to define something called a poly sequence, P sub infinity, which is defined as a tensor product of infinitely many 1-qubit polys, or equivalently, we can group them together in sets of n, and then it's the same definition. We're just taking a tensor product of of infinitely many n-qubit polys at a time. So now we get to actually talking about quantum convolutional codes. So, or encoder. So a quantum convolutional encoder, we'll call it U, maps n minus k, it maps m memory qubits, n minus k ancilla qubits, k logical qubits, to n physical qubits, and m new memory, an m qubit new memory poly. So basically, each of these are going to be poly operators, and we map one to the other using this encoder. And the condition is that each time when we go through the output, the memory from the previous one goes in as the memory input for the next iteration of the encoder. So in particular, the encoder should work in the following form. I'm going to be following a initialization, propagation, and termination behavior for this procedure. So at first, it should take the m-qubit identity, z, I, k, and turn it into some member of our generator set and some new memory state, G. And then it should propagate so that it turns the memory state from the previous step, n minus k, k plus 1, g, I, k plus 1. And then it should end eventually in the identity state. Basically, it takes no effect on the memory, does its processes, and creates stabilizers along the way, and then at the end returns no effect on the memory. And following this, we could kind of turn this process into a graph instead of just a bunch of equations, where we say that we turn the graph so that each vertex is some memory poly. So, for example, on one memory, 1 qubit long memory, we have like x, y, and z. And then the edges are basically sets of inputs on the ancillas and the logical operators that map you from one memory state to another. And this is called a state diagram. Okay, so this is basically the definition of a quantum convolutional encoder. At this point, we get to finally talk about the bad news related to them, which is that for any recursive quantum convolutional encoder, the process is going to be catastrophic. So first, I need to quickly define what those mean. So the first thing is that being a catastrophic encoder basically means that if you apply some logical operator, which is a third register in our ket, it causes an undetectable error, and that this error can continue spreading throughout your system as you continue encoding information. And then recursive is defined as, so within our state diagram, so I'm just going to draw like a rough idea of what a state diagram would look like. We have a path in it, and we call it admissible if the first edge is not part of a zero physical weight cycle, which means all the H operators are the identity. And then we have some sort of non-zero weight. All right, so from a vertex, we have a zero physical weight loop, and we also have the option of taking some path that is not a identity operator on the physical qubits, and also the option of going along some route that doesn't have any sort of, that has some sort of logical operation as well. So that's basically what a recursive encoder is. So I guess at this point, I'll talk about catastrophic behavior. So the main theorem is that recursive quantum convolutional encoders are catastrophic. Proving this in this direction is a little more difficult, so instead we're going to prove the contrapositive, which says that, basically if you just flip the logic around, if a quantum convolutional encoder is non-catastrophic, then it is non-recursive. So in order to do this, we need to define a few more things. So first thing is a zero physical weight cycle. So in our state diagram, if we have some sort of cycle within it, where all of the physical operators are the identity, then this is a zero physical weight cycle within our state diagram. And sorry, one moment. Let me make sure I flip the page in the right direction. Okay. So the set of all these zero physical weight cycles is a group, which we will call P sub 0. Or it's a subgroup, within the entire state diagram. And so that's our first definition. The next one is a standard path. So we've got our state diagram, and a standard path basically says we're going to go from some vertex and move to some other vertex, and then continue going on, picking new vertices using different inputs for the ancillas and the logical operators to move along the graph. So in general, this will do something like it'll map the state M0 with some stabilizer S0 with the identity and turn it into some initial physical poly and some initial memory poly. And then it'll propagate with the action turning the ith iteration memory poly into the I+1 physical and the I+1 memory state. All right, so this is just in general standard path, and now we distinguish two types of standard paths, the finite version and the infinite version. So finite, it means that, as you would expect, there's some termination, which is, it'll basically map it into a physical operator at time t, and then back to the identity. Or you can have the infinite, in which case it just keeps going on and on, cycles through, or it goes through a whole bunch of different memory operators. So first thing that I want to note is that the finite standard path is a group, in that if you define each standard path by the first state that you input, you can multiply two of them together, and you'll just end up going through one cycle through the memories and another cycle both at the same time, and eventually you're going to return to the identity at the same time for both. The infinite one is a little more complicated, and it's not directly a subgroup. So we're going to call the finite one f sub 0. And then the infinite one, though, something to note is that if M1 is in this infinite set and M2 is in F0, and we take M1 dot M2, this is still going to be infinite because M1 has an infinite standard path, and composing it with M2 is also going to be infinite. So then this is in the infinite set. But then if we take M1 dot M2 dot M2, this is equivalent to just being the identity. And so then this has to, wait, hold on, one moment. Oh, sorry, no. One moment. What happens here? This becomes finite. Wait, hold on. I feel like I made a mistake here. Oh, okay. Taking these together, we end up with a finite standard free path, or standard path, because the composition of these two form some sort of direction, and this one forms a cycle, and so you end up back at the identity eventually. Okay, so those are some definitions. And also, if we quotient out the finite standard path group out of the infinite set, so if we define I0 as the infinite standard path set without F0, this, on the other hand, is a subgroup. And between this I0 and F0, we have the entire state diagram for our system. Oh, okay. All right, so I guess from here I'll do a little bit more loose. So what I want to show basically is that the zero physical weight cycles is equivalent to what's called the centralizer of the the finite standard path group, where the centralizer is basically defined as if S is a subset and G is a group, it's defined as a set of elements within G that commute with all the S within the set. So this is shown through a variety of techniques. So first thing is that if you are an encoder for the quantum convolutional code, should be composed of Clifford gates if we want it to be efficiently implementable. And so because it's written as Cliffords, it means that suppose that we have let's suppose that we have 2 input sets and 2 output sets from the convolutional encoder. Then it means that the commutators of the inputs should be equal to the commutators of the outputs because the Clifford group preserves commutation relations. All right, so then from here, we can show that P0 commutes with F0. So basically, so to show this, basically we have some, all right, so we have that the logical register and the physical register and the stabilizer registers all commute because for the physical one, the physical registers are all the identity, and for the finite path one, the stabilizers are all, the logicals are all the identity. And the stabilizers are all going to commute because they're only tensor products of the identity and the Z operator. So all that we need to worry about is whether the memory states commute between those in a member P within P0 and some F within F0. So basically, for some P in P0, we can write the memory path as this. Mi P goes to Mi plus 1 P. Mr goes to M1. And for the member in the finite standard path, we can say that this is M0 goes to M1, and the same idea here. Now, if we want these two to commute, we need to actually just do the commutations. Each of these entries are Pauli operators, and we notice that each value at the output appears one time in the, each memory state appears one time in the output and one time in the input. So overall, when we commute them, we're going to have each of those commutations appearing twice. So the overall phase will be something like -1 to the 2 times the sum of the commutators of F, M, K, P, plus the commutator of the final state, this goes eventually to the identity, of this guy with each of the outputs from the P. So that's identity with Mi P, sum over I, and then also sum over J of M0. M0F with MJ P. So this is clearly 0. And then from the earlier statement that the commutators of the inputs and the commutators of the outputs have to be equivalent, this must also be 0. And then this is just 2 times something that's in the that's a natural number. And so overall, this is a 1 phase for the commutation. And so it's clearly the case that P0 commutes with F0. And what this basically says is that then P0 has to be a subset of F0. To show the other way around, I would encourage you to read the paper that I have here. And it turns out that F0 is a subset of P0, C of which means that the centralizer of F0 is equivalent to the 0 physical weight cycle subgroup. So from here, this basically leads to the final conclusion that because these are equivalent to each other, then the theorem. Then the recursive quantum convolutional encoder has to be catastrophic because you basically apply one of the lemmas that I prove along the way that basically basically as you move along the states in F0, you end up always commuting with elements in P0. And so they, basically whenever you cause an actual error, whenever a logical operator occurs, it causes a catastrophic error. So then I guess I'll very briefly, before ending, talk about turbo codes. So basically a turbo code turns a, well, this is page 8, okay. Turns a, so in general, we'll have what's called a quantum interleaver, which maps polys into permutation indices of the polys with some symplectic matrix K. And so we'll call this operation capital Pi. And overall, a quantum convolutional encoder is a, basically you use quantum convolutional coders as these symplectic matrices Ki, and then you apply it within your turbo code. And so the restriction on recursive quantum convolutional encoders being catastrophic means that if you want to use or create a quantum turbo code, you can't use a recursive quantum convolutional encoder, otherwise it's going to not work out well. So I encourage you to read this or ask me for a copy of it if you want to see the other lemmas for showing the other direction around. Also a little bit of generalization toward Qtit's version of turbo codes. Okay, that's the end. Questions, I guess.
So,
yes.
Can you maybe quickly draw kind of a schematic circuit diagram for a convolutional encoder and turbo code?
Okay.
That might help people.
So, okay, this word was not used. So in general, this is a quantum convolutional encoder. So we've got some input, memory I, an output, memory I plus 1. We input some ancilla and some logical stuff, and we output physical. And then afterwards, we then can do another one, and we make sure that the memory input for this next one is the same as the memory output for the previous one. And then for a quantum turbo code, let's see. So you have some input encoder. Let's see. So this is pi. Basically, the idea is you apply one encoder, you apply a quantum interleaver with your quantum convolutional encoder, and then afterwards you apply another encoder, and that works as a turbo code encoding.
Okay. So, very quick question. So why are these things useful?
They would, in principle, they would be able to, I mean, it's just another encoding scheme. Like, I mean, there are other options that could work, but the more options, the better. And it, in principle, is a very efficiently encodable scheme.
Okay, thanks.
All right.
Okay, awesome. Hey guys, so my name's Andrew, for those of you who don't know me. And I'm going to be talking about the complexity of decoding quantum stabilizer codes. And I'm going to first start with a review of complexity classes. I'm not sure how much you guys know, so I just wanted to at least say it pretty quickly. The class P is essentially all decision problems, so problems for which there's a yes answer or a no answer, such that there exists a polytime algorithm which decides it. So an algorithm which terminates in some polynomial number of steps in relation to the size of the input, and will say yes or no about whether your decision problem is true or false. The class NP is a similar class, but it is larger. It contains P, and it's the class of problems for which a yes answer can be verified in polytime using some polynomial-sized certificate. So if you have an oracle for one of these things, it will tell you, oh, yes, and it will give you a certificate confirming that it's yes, or it'll just say no, but you can't prove it quickly. And then the one important thing, which will come up in this talk, is a polytime reduction. So polytime reduction is a method of, I guess we'll use it as a method of proving that two things are related in some way, at least the speeds that you can calculate them. And if Q1 and Q2 are decision problems, we say that Q1 polytime reduces to Q2. We'll write it as this less than or equal to P, Q2. If there exists some algorithm, some efficient polytime algorithm such that, or which uses Q2 as an oracle, or uses an oracle for Q2. So you have some oracle which tells you, yes, Q2 is true, or no, Q2 is false, and it tells you that quickly. So it uses an oracle for Q2 as a subroutine. And then this algorithm decides Q1. So if using an oracle for Q2, you can efficiently decide Q1, we say that Q1 polytime reduces to Q2. And essentially what it means is if you can solve Q2 efficiently, then you can solve Q1 efficiently. Or another way that we'll look at it is the way that we care about it is this meaning of NP complete. So a problem is said to be NP complete if it is in NP and any problem in NP polytime reduces to it. So traditionally, SAT is like the biggest example of this, but there's also like traveling salesman problem and a lot of problems that people have heard of. So they're a very important class of problems, and solving any of them efficiently would mean that P equals NP, which is thought to not be true. So that's probably not the case. So these problems are thought to be very difficult to solve and very intensive. And then there's also something called NP hard, where it's a problem which is at least as hard as any NP problem. So if you can find some NP complete problem which polytime reduces to it, that means you probably can't solve it efficiently. So using these ideas, we want to first talk about the classical case of what we want to talk about for the quantum analog of. So the general problem in the classical case is going to be you have C, which is an NK linear code with some parity check matrix, H. So the parity check matrix is going to be n by n minus k. And the scenario is let y be some received vector. So someone sends you a message, and it comes to you as y, but it has some errors in it. And then let s be the error syndrome. So in the classical linear code case, the error syndrome is going to be given by y multiplied on the left of h. And the goal is, so find the nearest code word, or the most likely code word that was sent. Which in other words is saying find the code word x equal to y plus z naught, such that z naught is the minimum of all the z's which could have been errors, essentially. So this is going to maximize your probability of decoding correctly. So I wish I had time to go through the whole classical proof, but I definitely don't. It's a really pretty proof, though. And the basic idea is they create some decision problem, which we'll be using later, called coset weights, or cos, where your input is a binary matrix A and a binary vector Y and some weight or some size W, which is just an integer greater than or equal to 0. And what you want to do is decide whether there exists a vector x such that x equals w, so the Hamming weight of x is w, and xa equals y. Now, I'm going to modify this ever so slightly. This is not the original proof, but the proof that a similar result, which is also shown to be NP-complete, is that you can do this for x, size of x less than or equal to w. And so Berlekamp, McAleese, and Tilburg go through this proof and show that this problem is NP-complete by using a reduction method. And McAleese, later in that same year, actually found out that he can use this to create code-based cryptography. What's up?
What did they reduce it to?
So they reduced it to the 3D matching problem, which I don't have time to explain, but I can explain it after if you want. So McAleese realized that this could be used for a type of cryptography. So he defined in the paper later that year code-based cryptography, where you take these linear codes which have efficient decoding, GAPA codes in this case, and you transform it by linear operations into something that resembles a random linear code. And then that is your public key. And someone who wants to encode something, they'll code it as a code word in this supposedly random code, and then apply some small error to it on purpose. And when they send that to you, anyone who intercepts it, decoding a general linear code is NP-complete. So it's thought to be that they can't decode it at that point. But you can undo the linear operations, take it back to a GAPA code, which you can decode efficiently. So this was great motivation for looking at these sorts of things. And that kind of led people to look at the quantum side of things. I mean, quantum stabilizer codes are very similar to classical linear codes. So they wondered what happens in the quantum case. So that's what the paper that I'm presenting on looked at mainly. And I'm just going to go through a little bit of notation. So GN is just going to be the Pauli's ignoring phase. But some important things, which will show up a lot, is S, which is their stabilizer group, is they just define it using these operators, which they call Z1 through Zn minus k. And they do this so that they can use the commutation relations between logical z's and logical x's that we typically think of. And you can extend this to Zi, xj, which is a generating set for all of Gn. So there's some canonical extension following the commutation relations once you've established a stabilizer. And from this, they name two specific groups. There's L, which is essentially all of the ones from n minus k plus 1 and beyond. And then there's T, from 1 less than or equal to j less than or equal to n minus k. And what they notice is that these represent logical errors on your code word in your code space, which you cannot correct because these operators commute with all operators in the stabilizer. But these represent logical errors which you can correct because they will anti-commute with one of the elements of the operator, and therefore you can identify it uniquely. So using this, They want to talk about the quantum maximum likelihood decoding is essentially what they call it. And so given some error syndrome S, it corresponds to some error in T, which you can recognize. And the strategy is to find some error E, or some error in the set L called E, such that the sum over all elements in the stabilizer of the probability of getting P, E, and then T is maximized. And this will minimize the overall probability of decoding it incorrectly, which maximizes the probability of getting the actual decoding. And they also notice that so this is for the possibly degenerate case. If you're assuming that there's no degeneracy, then this is just finding E and L such that probability of E times T is maxed. So now I'll go into a little bit of what all of the proof relies on is the symplectic formalism. And recall that you take I to 0, 0. Here they're going to do Z is 1, 0, whereas I believe in class we did Z is to 0, 1, and therefore X is to here, 0, 1, just so you're aware. I didn't want to change all of the notation from the paper. But using the symplectic formalism, they want to come up with a symplectic code which is analogous to this quantum code. And they define that as let some stabilizer be symplectic vectors alpha 1 up to alpha n minus k. And then using the same commutation relations, you can extend these to a basis alpha 1 through alpha n, beta 1 through beta n. And then you're going to let H, your parity check matrix, be the matrix with row I equal to alpha I. And then C is going to be all elements which are, when you take the symplectic inner product with the matrix, you get out 0. And this is also, if we notice, this is equivalent to just the span over all alpha 1, or alpha n minus, alpha 1 through alpha n, and beta n minus k plus 1 to beta n, all the things that commute with those rows. And then from here, they define 3 things, which are C perp, which is the span of alpha 1 to alpha n minus k. They define L, the span from alpha n minus k plus 1 to alpha n, and beta n minus k plus 1 to beta n, and T, which is a span of beta 1 all the way up to beta n minus k. And it's pretty easy to see that you can simply take these, the C perp, and identify it with the S. And you can take the L and identify it with the script L. And you can take the T and identify it with the script T. And all of the commutation relations will work out really nicely. And everything will kind of satisfy the same properties. So in this formalism, you end up getting that given an error syndrome, S, an error syndrome uniquely corresponds to some symplectic vector gamma 3 in T, kind of like it uniquely corresponded to some T in T over there. And therefore, the strategy is to find some gamma 2 in L such that summing over all elements of C perp, which is equivalent to your stabilizer now, and taking the probability of gamma 1 plus gamma 2 plus gamma 3 is maxed. So this is equivalent to
5 minutes.
5 minutes? Okay. So I am not going to have time to go through both parts of the proof, but I will at least state, so they're working over a poly channel where they're assuming that the errors occur on Z errors and X errors both occur independently at random with probability P, which means the probability of a Y error is P squared, which is maybe not the most realistic, but it helps with these results, and other people have generalized this to more cases. So therefore, the probability of some error gamma in symplectic form is going to equal P to the weight of gamma times 1 minus P to the 2n minus weight of gamma, where here weight of some symplectic vector, zx, is defined as just the Hamming weight of z plus the Hamming weight of x, based on our poly channel. And here we get the, I'll only state one of them, the quantum maximum likelihood decoding. This is assuming no degeneracy. But we assume we get some input, which is our basis, alpha I, beta j, which satisfies all the aforementioned properties, and some vector gamma 3 in T. And we want to output some vector gamma in L, minimizing weight of gamma plus gamma 3. Now here, the reason why we're minimizing the weight of gamma plus gamma 3 is because since we're assuming no degeneracy, we're to this case where it's the probability of ET, or in the new case, you're maximizing the probability of gamma plus gamma 3, which is the same as minimizing this weight in this case, based on how the weight function is defined. And to prove that this is NP hard, you can give a reduction. And I'm not going to have time to go through the full reduction. But what they essentially end up doing is they create these matrices of symplectic vectors. And AI is just the ith row of this matrix. And beta I is going to be the ith row of a similar matrix. And what they end up doing is seeing that this defines C perp, C, and T, and L in all of the ways that you would want to define it for the original problem. And then the proof would go something like this, where if you want to show that cos polytime reduces to QMLD, you would look at given A, Y, M, and an oracle Q for QMLD. You construct this basis in that way, and you and define gamma 3 off of it. And then from there, you can give these things to the oracle, and the oracle will give you some vector gamma hat, which is the value at which this weight of gamma plus gamma 3 is minimized. And then using properties of this weight function, you can show that weight of gamma plus gamma 3 and weight of gamma plus gamma 3 is just going to be, it ends up being the minimum over all V such that AV equals Y, and it's the minimum Hamming weight. So in other words, if this value is, this will give you the minimum value at which this vector satisfies that property. And if you look at cos, that's exactly what we wanted. We asked, does there exist a vector of smaller than that? And it turns out, yes, if and only if the thing that this oracle prints out is less than or equal to W. And that's all I have time for. Thanks. Yes?
So this is the same like we earlier in the beginning. So the linear codes have to have NP decoding?
It says that a general linear code must have NP decoding. As I said, there are GAPA codes which you can decode quickly, and you can use that for crypto systems. So there are some special classes of codes which, there are efficient decoding systems. But for the general, like if you choose a linear code at random, it would have an inefficient decoding.
I see, and this would just be like for a random quantum
yes,
linear code.
Yes. And also, this one is very specific also to the channel model that they use, how they assume the errors are distributed, and stuff like that. There are a few other papers which I actually wrote about in my final project that kind of generalize it to more and more different situations.
So one of those situations is the depolarizing panel?
Yes. So that is Hyo and Liu, I believe, wrote about, they showed that it's NP hard in the depolarizing channel, and also assuming the general weight rather than the Hamming weight. Or, sorry, the general weight rather than the weight function I defined on symplectic vectors up there.
Maybe you can comment on any interesting possible future open problems?
So I think the biggest thing is I couldn't find any papers that actually gave a quantum crypto system based on these things. And they may exist, I just didn't come across them. And I would really like to see kind of what the analogous quantum crypto system looks like. But also I don't think any of the papers have answered the question full generality, although Iyer and Poulin do a very good job. So.
Okay, so let's move on.
Good afternoon, everyone. Yes, I'm Dinakaran. And as Andrew said, like decoding algorithms for surface codes or in general stabilizer codes is NP complete, but we are going to, we also found that surface codes or we have to find some sort of stabilizer codes which have to be efficient for decoding. Otherwise, it's not easy to implement quantum error correction. So one of the things that has been that we have studied in class is surface codes, which have good properties for efficient decoding. And I'll just have a very simple diagram, which I keep using throughout this talk. I will have a 2D toric code example where the qubits are on all the edges. Let's also say there's no boundaries. And the X stabilizers are, say, the vertices. So these are the X stabilizers, and the Z stabilizers are measuring the plateaus, as we did in the talk. Okay? So in this, also, all the papers that I'm going to talk about here also assume that the errors in each of the qubits are independent and identically distributed. And also for this talk, I will just focus on the Z errors, and hence we'll just focus on the X stabilizers. Yeah, so that will be one simplification. And what is the thing that we have to do? What is the decoding algorithm has to do? The decoding algorithm is given, say the errors are here, here, and say here, here, and here. So these are the phase flip errors on these qubits. Then every phase flip error introduces or makes this syndrome vertex and this syndrome vertex -1. So if there's a phase flip error here, this and this are -1, and this phase flip error, and this makes this syndrome vertex and this syndrome vertex -1, so this goes off. So overall, what happens is that we have the -1 syndrome vertices on ends of an error chain. And say here, we get -1 here. Okay, maybe I want to say there is here. So we get syndromes here and here. So these are the -1. So the goal of the decoding algorithm is, given these syndrome vertices, we have to find the correction operator. which amounts to, say, finding the error chains, okay, up to a stabilizer. So this will be the goal of the decoding algorithm. And also, we want it to be like at least as fast as the cycle speed of a quantum computer so that we can correct the errors, or at least note the corrections as we find the stabilizer measurements. Okay. In this talk, I will mostly focus on, there are like multiple kinds of decoding algorithms that has been proposed in the literature. I was thinking about going one of them in detail, but I felt that like for the background that we have covered in the class, it's better to like go at a high level on like a couple of them instead of going in one of them in detail. So I will go over at a high level for the minimum weight perfect matching based decoders and the union find based decoder algorithms. So what is minimum weight perfect matching? Or first, what is matching? Okay, matching is okay, if say you're given a graph of say these are the vertices and say we have edges like this. So this is the graph that we are given. A matching is just a subset of vertices such that, subset of edges such that every vertex is covered at most once. So, I mean, if we just have this edge, this is already a matching because these vertices are covered once and these vertices are covered like at most once, 0 times. And so what is a perfect matching? A perfect matching is when we find a matching where every vertex is covered at least, exactly once. So we have, say let me take the graph that's formed here, which is, say we have this, and this. Okay, so let's say like we have these vertices V1, V2, V3, and V4, and let's say we have like a sort of a complete graph. Maybe it's too much, but yeah. So let's say we have this edge and this edge. This is a matching because every vertex is covered exactly once. So this is like a perfect matching, okay? And minimum weight perfect matching involves finding a minimum or a perfect matching where we have where the sum of the weights of all the edges is minimum, okay? And that seems like I mean, once we are given syndrome vertices, it seems like minimum weight perfect matching is like the actual problem that we want to solve. If you have a graph containing all the vertices that are -1 vertices, and say the edges correspond to the distance between each of these. So for example, distance between this and this is 2 because there are like, say, 2 qubits in between them. And similarly, like if we plot distance between every pair of vertices, say, these two are separated by 1, 2, and 3. So V3 and V4 are separated by 3. And similarly, if we go on this way, minimum weight perfect matching seems like seems to give us the error chain, let us find the error chain that we want to get as the decoding, as output of the decoding algorithm. Okay? And also, just note that a perfect matching exists only when the cardinality of the vertices is even. So, and that is that's the case here because every like a step error chain has -1 syndromes only at the end of the error chains. So for every error chain, we have a pair of -1s. So the cardinality of this set is even. So, and yeah, we can find the perfect matching, and minimum weight perfect matching is like a good way to solve this decoder problem. And starting from the work, like the first work we studied the decoding algorithms for surface codes. It was by Dennis, Kitaev, Landell, and Preskill. And like even that paper, they proposed minimum weight perfect matching as like a good way to solve this problem. Okay, let me just give a brief overview of the way that you solve minimum weight perfect matching, so that we can see like what's good or bad about that in the application for decoding for surface codes. So, okay, Edmonds algorithm is like a famous way to solve this problem. I'll just give like a 2-minute overview of that to see how that's useful for doing this. So in Edmonds algorithm, we always maintain a set of like what I call matched edges, which initially is a null set, but you populate it as you go on. And then you can say also maintaining a set of matched vertices. I'm like abusing the notation here, but in general, like the set of matched vertices is just all the edges covered, all the vertices covered by the edges here. So if you have, say, this edge in the edge set, then the matched vertices will have v1 and v2. So that's just the notation. And every step of Edmonds algorithm, what it does is you start with some arbitrary, say, unmatched vertex, and then you look at the graph, the whole graph from this vertex point of view. So what you essentially do is you start with some particular unmatched vertex as the root, and then you start constructing a tree with this vertex as the root. And then what the property that you want from this tree is that every path from root to leaf is alternates between matched and unmatched edges. So you start with a particular unmatched vertex, and then you construct a tree starting from this vertex such that every path from root to leaf contains alternating between unmatched and matched edges. Okay? And I just want to tell this because you don't want to know how this works. I mean, you have to do something more when there is odd cycle in this graph, and you have to do something even more when there are the edges are weighted. But the thing that you want to get from this is that the running time of this algorithm, in the worst case, it involves going through all the vertices in the graph. And for each of the vertices, you have to go through possibly all the edges. So if you analyze the Edmonds algorithm, the running time is O of sides of edges times O of v square. And there have been follow-ups proposed doing something more complicated, and you can reduce it to O of size of e times square root of size of v. But still, there is if you have a complete graph, you still have O of n to the 2.5 kind of algorithm. Okay? So, but the thing is, we don't need to use the full power of minimum weight perfect matching for general graphs, because there are some special properties that are associated with this thing. So there is actually a bad thing is that for every round of stabilizer measurement, we get new errors coming in. It seems like we have to recompute this graph, the whole graph for every round of measurements, because we have new vertices coming in at every time and they change. So that's actually a bad thing, because we have to recompute this whole thing, and every iteration takes n to the 2.5. But there are some good things, is that since the error is bounded, say every z occurs with probability some pz, the size of the error chain going length L exponentially reduces in the length of the chain. And also, the next statement is slightly non-trivial, but that gives some intuition why there won't be error chains close to each other all the time. So if there is an error chain of length L, 1, then the probability for the error chain of length L2, which is at a distance L1 plus L2 from each other, is slightly small. So, I mean, the main intuition that I want to give here is that the error chains won't be very long, and also two error chains will not be very close to each other a lot of time. So, given these properties, the consequences are that in Edmonds algorithm, the alternating tree, I mean, this is called alternating tree, and the depth of this tree will not grow beyond a certain extent. So this led, some experiments, they partition this whole graph into some constant sizes, and then they apply Edmonds algorithm for each subcomponent separately, and then they either merge the trees along the boundaries in the nearest with the nearest component, or they just just focus on parts of the graph, parts of the here torus or something, and then apply minimum weight perfect matching locally. And when they do it this way, they get O of n, they still have the O of n square complexity for like constructing this graph and do some things, but it's like slightly reduced. But there's like a potential for more parallelism, and they achieve like a threshold of 10.3% for minimum weight perfect, like when doing this way. But still, the question here is, do we really need the full power of minimum weight perfect matching here? Okay, because you still, as I said, you have to compute the distance between every pair of vertices. So that's already like O of n squared. And so that led like a recent result to use the locality in like slightly more pronounced way, I would say, with a slight compromise in the threshold. And what they do is, if you have the set of, say, a poly errors that's given to you, you want to, or you're just given this like poly errors, or the syndrome vertices for the poly errors, and given that, you find like a slightly longer span such that all the poly errors are included within that. And then you apply erasure decoder on that set of qubits. So I'll say this in a little more detail. So what is erasure? Like, what is erasure channel? It's like, you can think of it as applying like a random poly error, but you know the location where the random poly error is applied. So that's erasure. Okay? And what erasure decoder usually does is, you're given like the syndrome vertices and also the qubits where there are erasures. Say there are like erasures. Yeah, you know where the erasures are? Yeah. Oh, sorry. Okay. Yeah, you know where the erasures are. So for erasure decoder, you are given like the syndrome vertices as in the poly error decoders, but you also know where the locations of the erasures are. So that lets like some people to have a linear time decoder, like O of n decoder, if you're guaranteed that there are only erasures in your, if you just allow for erasure errors. So this work, what they do is, they try to convert, or they try to have a reduction from the poly errors to erasure errors. And how they like do at a very high level is, given the syndrome vertices, they try to like get a slightly longer span, but such that you can, when you apply like a correction operator for the poly chain, error chain, lies entirely in the extended span. Okay, and how they do it is, okay. Oops. Maybe I'll. Yeah, so if we have error syndromes here, say here and here and here, what you form, like wherever there are error syndromes, you form like a cluster, say initially with wherever there are like -1 syndrome vertices, and then we identify, like, so the way that I have drawn, every cluster is a odd cluster because there is only one -1 syndrome vertex in it. So what you do is, at every step, you also, okay, so you maintain like additional, okay, so at every step, you grow every odd cluster by a half edge. So at the first step, you grow this cluster this way, like it also comes up here, and you grow this cluster by half edge, and you keep doing this, and if at any point, so this cluster merges with this cluster in this way, this point, because yeah, this grows halfway here and this grows halfway here, and like if two clusters merge, you keep growing clusters by half edge at every time cycle, and when two clusters merge, you check whether they are even, and if they are even, you just treat them as erased, and then you keep doing that for all the odd clusters remaining. So the essential thing that you do is you keep growing the odd clusters by half edge at every time step till you run out of all the odd clusters. Okay? And the reason why you do that is because if a cluster has even number of -1 syndrome vertices, then we can prove that the whole the correction operator for the poly errors lie entirely within that cluster. Okay, so that's the intuition. We keep doing this, and so this is heavily used growth of clusters and maintenance of clusters heavily uses the data structure called union find, and the runtime for that is almost linear time. So I don't think I have time to explain or give a overview of that thing. But given that we can grow the clusters to reduce it to erasure channel in a linear time, and then we have linear time decoder for erasure channel, we can find the error chains in almost linear time. And I told that the threshold is 10.3 for if you use minimum weight perfect matching based decoders. Here, for the same set of parameters, it's almost 9.6 or something. So we have a slight reduction in threshold, but we still have this. And then, so these authors do not really talk about the parallelism in this aspect, but if we make similar sort of claims as in the minimum weight perfect matching and say that, we can split the things into constant parts and then apply the cluster growth in each of the constant things in parallel between all of the components, then it seems like this sort of algorithm is more amenable to that because growing a cluster does not require the global information. It just grows locally till you cross the boundary to the next one. So it seems like this sort of algorithm is more suitable for parallel growths. So it seems maybe we can even do better than OFN if we have multiple computers running. So in summary, I just summarized two the ideas in the decoding algorithms for surface codes, one using minimum weight perfect matching and one using the union find data structure and using erasure decoder, and some ideas about how to run these in parallel and just focus on the local components. And these heavily assume that you have IID errors, and also they have it's not clear whether there are some other works which I've looked at, but I mean not in detail. They support a more robust noise models, which is more than IID errors, but they don't have very good performance. So maybe one good future direction will be to extend any of these to support more robust noise models.
So this was for Z errors. So what do you do if you have X errors as well?
Oh, you just consider the dual lattice and then do the same thing actually.
Okay. At the beginning, I think you said you want the amortized runtime to be as fast as a cycle of quantum computer.
Yeah, I think at least in the worst case, ideally you want the decoding to complete within this, but at least you want the amortized case to.
So for all your thresholds and all your complexity, you're talking about runtime in the worst case, though, right?
Yeah, that's true.
Okay, so you don't. Do these algorithms have things where you can cut off at a certain point, or
at least they don't talk about this in the papers. I mean, the papers that I've read.
So if you have 1 milliseconds for each cycle of your superconducting quantum computer, right? If your algorithm's not done, can it give the most optimal answer at that point? Or do these algorithms need to run to a completion for me to get?
So yeah, that will correct part of the errors, at least in this case. For all the even clusters that you have, that corrects the part that you already have even clusters for. But I think we have to calculate the threshold and run the simulation, see what threshold they work on if you limit the runtime. I think it's hard to make claims without. But yeah, even if you cut off at a certain point, there is a chance. I mean, you do correct some errors, but it's not clear how to quantify it. Independent.
Okay, thanks.
Okay, hello everyone. I'm going to talk about short Presqu'île security proof of QKD protocols, which basically use properties of quantum error correction. Let's first consider the quantum key distribution setting where we have two parties, Alice and Bob, who are basically separated, and they can communicate with each other through quantum channel and an authenticated classical channel. And we have also another party, Eve, with big ears, who can basically eavesdrop everything on classical channel, but cannot change anything on the classical channel, and have access to the quantum channel. And the goal is that Alice and Bob wants to generate a secure key by communicating through these two channels, and so that the keys are secure in a sense that Eves cannot get any information about the key. There are many known QKD schemes. One simple one is Low-Chow protocol, which basically uses entanglement distillation to produce a key. And the good point is that its security proof is pretty easy, but the problem is that it needs to use a quantum computer in a sense that the parties needs to have quantum memories and perform quantum operations. And another well-known quantum key distribution setting, quantum key distribution scheme is BB84, which is basically the first scheme proposed in 1984. This scheme is easy to implement. It only needs preparing the states and measuring them, and there's no need for quantum memory. But the problem is that its security is pretty difficult to prove. Basically, the first proof came after 12 years, and it's by Mayers. But this proof was pretty complex, and in 2000, Shor and Presqu'île gave a simpler proof which uses relation between CSS code and entanglement distillation to prove the security. And this proof method has been used to prove the security of many other QKD schemes like 6-state protocol, B92, continuous variable QKD, and so on. So in this presentation, I'm going to basically describe this proof scheme. So in their proof, they start with a modified version of Low-Chow protocol, which can be shown is going to be equivalent to the BB84 protocol, and they show that that protocol is secure, and which implies the security of BB84. So let's see what's the main idea of this modified Low-Chow scheme. So if Alice and Bob shares let's say m pairs of EPR pairs, then they can separately measure their halves in the standard basis, and they will get some random key. And the point is that if the state they share is pure, then Eve does not have any information about that state, because Eve's state is basically in tensor product with this EPR pairs. But if they share a state which is close enough to EPR pairs, then they can use entanglement distillation to distill some perfect EPR pairs, or at least almost perfect EPR pairs, and then they can use that to get almost secure key. And in order to share EPR pairs, Alice can just prepare EPR pairs on her part, and then sends second halves of EPR pairs to Bob. But then since Eve has access to the quantum channel, she may get some information, and she may disturb this EPR pairs. But in order for Alice and Bob to determine how this state is disturbed, they're going to choose half of these pairs randomly, and they will measure those pairs and see compare the results and see how many errors they have. If the error is high, they decide that Alice has lots of information about APR pairs, and if it's low, then they conclude that the rest of the rest of the states are close to EPR pairs, and then they use entanglement distillation to get perfect EPR pairs. Now let's see how they do entanglement distillation using quantum error correction. So suppose that we have an stabilizer code with generators S1 to Sn minus k, and logical operators x1 bar to xk bar and z1 bar to zk bar. So if Alice and Bob share a perfect n pairs of n EPR pairs, and each measure generators on their sides and get the syndrome error and correct it, their final state is the state here. And it's easy to see that this state is also stabilized with xj bar tensor xj bars and zj bars tensor zj bars, which means that this final state is basically the encoded maximally entangled state on k qubits. Now, if Alice and Bob share a state which is close to n EPR pairs, then by measuring in the stabilizer generators, they get some syndrome error, and by correcting that, they will get a state which is very close to the maximally entangled state. So using this idea, the modified low-Chow scheme looks like this. So Alice starts with 2 n EPR pairs. She picks some 2n bit strings and performs a Hadamard on each pair, on the second half of each pair, if BI is equal to 1. Then she sends second half of each EPR pair to Bob. Then Bob announces the reception of the qubits, and then Alice selects randomly n of these EPR pairs as check pairs, and also she announces B and these indices of these check pairs. So then Bob just undo the Hadamard application on the qubits he received, and then Alice and Bob both measured their qubits in their halves of check EPR pairs in a standard basis, and see if there are more than T disagreements or not. If there are more than T disagreements, they abort the protocol. Otherwise, they conclude that there are less than T errors in the rest of the EPR pairs, so they can use the stabilizer generators to correct those T errors and then get a state which is very close to a maximally entangled state. And so they can get, basically by measuring in the logical 0 and 1 state, they can get the key. So let's see a sketch of a security proof. So the first point is that by choosing B at random and applying Hadamard on the qubits, which has BI equal to 1, since Eve doesn't know B, then she cannot distinguish in which basis she should make the measurement. So if she makes a measurement, she will definitely disturb the state. Then Alice and Bob, in order to basically find the disturbance, they use check pairs. And again, since Eve doesn't know which pairs are chosen as check pairs, then if there are low noise on check pairs, it implies low noise on the rest of the qubits. And so after distillation, the state will be very close to a pure state, which means that Eve has very small information about the key he derives, and key the parties derive. So this shows that this modified low-Chow scheme is secure. Now, in order to reduce it to BB84 protocol, we need Alice and Bob to use CSS code. And so let's first recap the definition of CSS code quickly. So CSS codes are constructed using two linear codes, let's say C1 and C2, such that the dual code of C2 is a subset of C1. And the code words are defined as such, as we see in class, and stabilizer generators are Z operators on defined using check parity matrix of C1, and X operators defined using check parity matrix of C2. And an important property is that bit flip error correction in CSS codes is decoupled from phase flip error correction, which means by which I mean that Z generators can be used to detect bit flip errors, and X generators can be used to detect phase flip errors. Now, we can also define a family of CSS codes which have similar properties as CSS codes, and we define it for every n-bit string X and Z. We define these CSS of X and Z in this form, where Z only has effect on the phase and X has effect on the on bits. And now, so now using CSS codes, we can see how to reduce low trade-off scheme more. So first thing to see is that Alice performs measurements on her qubits in step 6 and 7, and in both of these steps, these measurements does not depend on what Bob has done before. So she can just do these measurements in the beginning of the protocol. So in the 6th step, Alice performs, for check pairs, Alice performs measurements in a standard basis, which will collapse Bob's state to ket0 or ket1 randomly. So she can just prepare ket0 and ket1 randomly at the beginning. And in step 7, so Alice measures her halves in stabilizer generators, and after her measurement, Bob's state would be in the random code word of a random CSS family code. And so instead of doing this instead of sending APR pairs and then doing this measurement, Alice could just prepare a random code word in a random family of CSS codes and just send that code word to Bob. So the CSS code-based protocol reduction seems like this. So Alice just at the first step, Alice just prepares a random code word in a random CSS code family. Then she creates n random check bits and puts them in n random positions. And the rest is the same, except that Alice should, in addition to B and indices of check bits, she should also announce the values of check bits and X and Z to Bob, so that Bob can be able to decode these states and get K. Now, an observation here is that if you look at this code word, you can see that in order to decode X, in order to decode K, knowing X is sufficient. So, and there's no need for Bob to know Z. So if Alice just does not send Z to Bob and just send X, then in Bob's point of view, Alice has been just sent a random code word K plus U plus X for a random U chosen from a dual code C2 pair. And so this protocol can be reduced more to the BB84 protocol, where Alice just randomly chooses some string A, 2n-bit string A, and also 2n bit string B, and she just prepares H to the PI on ket A, which is just basically choosing one of the 4 states, ket 0, ket 1, ket plus, and ket minus at random. And then she selects n random positions as check bits and random positions of A. And let's say A sub ch is the value of check bits, and A sub k is the value of other bits. So then just she sends the prepared qubits to Bob, and also she sends B and indices of check bits, and also the value of check bits. And then Bob undo the Hadamard application, and then Bob and he measures in the all of his qubits in the standard basis. So if the number of disagreements is greater than t, he aborts. But if not, then it means that the rest of bits Bob has is in fact AK plus some epsilon, which is the error. And with high probability, this error is the weight of this error is less than t. So what they do to basically correct this error is that Alice just choose some random code word in C1, and she sends AK plus VK, the random code word, to Bob. Then Bob, if Bob adds AK plus VK to his measurement results, which is AK plus epsilon, then he has VK plus epsilon. And since VK is in code C1, he can use this code to correct most of the errors in epsilon. Yes?
5 minutes.
5 minutes?
Yeah, a little bit less now.
Okay. And so he can correct this epsilon, and he can get a bit string very close to VK. And so then Alice and Bob just compute the coset of VK plus C2 pair as their key. So this is basically what BB84 is, except one thing, that is that if you look at this protocol, I said that BB84 does not need quantum memory, while here I'm assuming that after Bob receives the qubits, he keeps them and waits for Alice to send B. And so he needs quantum memory here. But this can be easily solved. This problem can be easily solved by just as if Alice, instead of preparing 2n bits at the beginning, she just prepare a little more than 4, so 4 plus delta n bits. And then when Bob receives his qubits, he doesn't wait for Alice. He just measures all his qubits at random, either in 0-1 basis or plus minus basis. And then after he receives the B, he'll look at he discards all the qubits that he basically measured in the wrong basis. And so it can be shown that with high probability, there are at least 2n qubits which are measured in the right basis. And so the rest of the protocol works for the same as before. And so in this version of BB84, there's no need for to have even quantum memory. They just prepare states, and as soon as each party gets a state, he measures. Okay, so as we have seen right till now that I showed that Low-Chow protocol is basically equivalent to this BB84 protocol, and since Low-Chow, the modified Low-Chow is secure, it implies security of BB84. Now let's look at 6-state QKD scheme. So it's very similar to BB84, except that instead of preparing one random state from 4 states, ket 0, ket 1 plus or minus, Alice prepares one of these 6 states at random. And basically, if you look at it, you can see that it's basically equivalent to that if she prepares ket 0 and ket 1 at random, and then she randomly applies one of the unitary operations identity t or t squared, where t is this identity defined here. So similar to the BB84, one can define entanglement distilling protocol, which can be basically reduced to the 6-state QK scheme, and the proof of security of that would be very similar to what we did for BB84, and basically Shor-Persky proof can be applied there. So I guess that's it. Thank you for your attention. Any questions?
So in QKD and say BB84, the last step is normally privacy amplification.
Mm-hmm.
So how is that appearing?
So privacy amplification. So basically, this step here is what they do at privacy amplification. So they basically eliminating this error in VK. So initially, Bob's measurement outcome is VK plus epsilon, and so in this step he eliminates this epsilon, and then he gets this VK. He can get this key. I mean,
eliminating the epsilon seems like an error correction step.
Right, which
normally you consider as a separate thing from the privacy amplification.
But here it also does the privacy amplification, if I understand it completely. So in privacy amplification, what we do is that so we want to make the state that the qubits that Bob has uncorrelated from what if has, right? And so by doing this error correction, we make this, the correlation between what Bob has and Eve has smaller.
Yeah, so I think it's actually really the last step, step 8, that's the privacy amplification.
Okay. Mm-hmm.
How do you compute the coset? You do it by taking some parities. That's what privacy amplification is, mm-hmm. basically. Yeah, and I mean, the way it's coming out of the quantum error correction code is the error correction is coming out of, say, the bit flip correction. The phase error correction is privacy amplification, basically.
Mm.
Any other questions? Okay, thanks.
Hello, everyone. My name is Thirapat, and today I'm going to talk about the tri-orthogonality, magic state distillation, and universal quantum computation without magic state. So in this presentation, first I will explain what the magic state is and why it is so important in universal quantum computation. And then I will introduce the tri-orthogonal code, which is the CSS code construct from tri-orthogonal matrix. And then I will talk about the distillation protocol by Browey and Ha. And then the idea of tri-orthogonal matrix can also be used to construct a universal quantum computation with only transversal gates and error correction. And this method is invented by Pesnik and Reichert, yes, and also another distillation protocol by Pesnik and Reichert. Okay. So first, I would like to talk about the computational model. So the set of all elementary operations can be divided into two sets: the O ideal and O faulties. So in the ideal, all operators are assumed to be perfect. And this includes the preparation of qubits in state 0 and application of unitary operators from Clifford group and measurement of measurement of an eigenvalue from Pauli operators x, y, or z. And in our model, the faulty operation is only the preparation of ancillary qubit in mixed state rho. So we would like to know what kind of density matrix rho can be used to efficiently simulate the quantum computation in the basis of O. So as we have seen in class, so that kind of ancillary qubit is called magic state. Actually, the magic state is an ancillary state which has two properties. The first property is called universality, which means the preparation of magic state along with the computation in the basis of O ideal can simulate universal quantum computation. And another important property is called distillability, which means if we have an imperfect magic state, we can purify it using only operations from O ideal. So there are many types of magic state. In the original paper by Bravi and Kitov, they introduced two types of magic state. So the first one is a T state there, which is the eigenstate of the that operator, which is, if you can remember from the class, is a operator that's swap between X, Y, and Z operator. And another state is H state, which is an eigenstate of Hadamard gate. So all state from the Clifford operator acting on T state is called the T-type magic state, and all the state from the Clifford operation on the H state is called H-type magic state. And another magic state that I would like to introduce in this this presentation is called Toffoli state, which is the state from the Toffoli operation on the state plus 0. And this state can also be used to simulate a universal quantum computation, and is also distillable. So the general idea of a magic state distillation protocol is that if we have a state A, which is a magic state that we want to distill, and we have an imperfect state rho, we will define the input error rate P to be 1 minus A rho A, like this. And in each round of a distillation protocol, the protocol will consume n copies of imperfect state, and it will produce another k copy of imperfect state, which is, we want it to be less noisy. So let P0 be the threshold value. If the input error rate is above the threshold value, in the distillation protocol, we will get another state with low error rate. But if the input error rate is below the threshold, at the end, the output will converge to maximally mixed state. So now, let's talk about the triorthogonal matrix, which is the main ingredients in this work. So this concept is introduced by Bravi and Haar. And if we have two binary vectors, we will define the f dot g to be the entry-wise product of f and g. And we will denote the f in the absolute value sign to be the Hamming weight. So for the matrix G to be orthogonal, let F1, F2, and up to Fm be the rows of matrix G. We'll find that the Hamming weight of Fi dot Fj for any pair of ij is equal to 0, and also the Hamming weight of Fi dot Fj dot Fk is equal to 0 for any triples ijk. So given the matrix G, we will have even weight rows and odd weight rows, and we can form the submatrix G0 and G1. So here's an example of a 5 by 14 triorthogonal matrix here. So we can see that first two rows here are odd weight. So we can define a G1 like this, and also the last three rows are even weight, so we can define G0 like this. So now we would like to construct a CSS code from an orthogonal matrix. So if we have a submatrix G0 and G1, we can define a linear subspace G0 and G1, means script G. which span by rows of G0 and G1, as shown before. And the CSS code, which is called triorthogonal code, can be constructed by mapping all elements in G0 to X operator and mapping all elements in G perp to Z-type stabilizer. There is a lemma that if a triorthogonal matrix G have k odd weight rows, so this CSS code has k logical qubits, and it's possible to choose the logical Pauli operators to be the operator from mapping rows of G1, which is the odd weight rows, and to these operators. And by that choice of logical operators, it's possible to define the logical zero state to be the superposition of a state from the vector in G0. And also it's possible to construct a coset Gx from any value of x to be the set of G from G0 plus x1, f1, x2, f2, and so on. And for any encoded state x bar, it can be written as superposition of state from vectors from the coset Gx. Okay. And now let's talk about the distillation protocol. So in this distillation protocol, we would like to distill a magic state A, which is a H-type magic state. It can be written as a SHS on state H like this. And in this notation, the T gate, which is different from the T that I previously explained, this T gate is actually the R pi over 8 gate, and S gate is R pi over 4 gate. Okay, so we know that a S gate is in Clifford group, but T gate is not in this Clifford group. Okay, and in the paper, Bravi and Ha proved that if we have a state G, which is a superposition of all vectors from the subspace G, then there exists a Clifford operator U composed of a control Z and S gate, such that U acting on a T and on G will give a encoded A state. And here is the protocol. So first, we will prepare a state plus state here, and then we will use the encoder of the triorthogonal code, and here we will get a state G. And after that, we will apply operation on every qubit. This operation is called, we can call it noisy T gate, which look like this. And this operation can be implemented by using an imperfect state A here and another Clifford operators and also measurement. And after that, we will apply a state U from the lemma 2. We know that a U composed of a S gate and control Z gate, so it commutes with all Z operators here. And at this point of the protocol, this state can be written as the noisy state of the state encoded A, where E is the defacing channel, like this. And after that, what we want to do is that we want to detect the Z error. So we will measure the X syndrome. And after that, we will post-select only the case that the syndrome is trivial. And after that, we will decode it. So at the end, we will get the state A. Okay. So in the protocol by Bravi and Ha, they construct a family of 3K plus 8 K2 triorthogonal codes. And the protocol involving this code will consume 3K plus 8 ancillary state A with error rate P. And at the end, we will get a K ancillary state A, I mean the same state, with error rate in the order of P squared. So we can see that we can get a better, more purified ancillary state from this protocol. Okay. Another application of the triorthogonal code is that Pasnik and Rickert shows that in the triorthogonal code, the control Z gate is transversal. So in their paper, they construct a triorthogonal code from the 15-qubit Hamming code by choosing the basis such that the transversal X and transversal Z on that code is a logical X and logical Z on the first encoded qubit. And by fixing another 6 gauge qubit, we will get a triorthogonal code, 1513 triorthogonal code. So in their paper, they prove that the transversal control Z is the encoded control Z. So here is the explanation. So first we will explain the state A, B, C like this, as we described before. And for simplicity, we will assume that the triorthogonal code have only one odd weight row. And after multiplying it here, we will get a term like this, which is a Hamming weight of G dot H dot I. And by the definition of the coset here, as described before, we can rewrite this term into these terms. And when we multiply together, we will get the first term with 3F here, and another term are all even weight terms. So since the code is triorthogonal, the even weight terms will give 0, and this term f dot f dot f is actually f, and is a even weight row. So at the end, we will find that by applying control Z transversally, we will get a -1 ABC here, which is the operation of the control Z. So we know that the Hadamard together with control Z are universal, which means that any universal quantum computation can be simulated using only H and control Z. In this triorthogonal code, we know that control Z are transversal, but H is not transversal. Because the triorthogonal code is not self-dual. And it has been proved that the universality cannot be achieved only transversal gates alone. So what we want to do here is that we want to apply the transversal H and then apply the error correction. So if we write the 15-qubit Hamming code, we have like a X-type generators and Z-type generators, and we will fix the gauge qubit for another 6 encoded qubit. We will find that by applying a transversal H, the logical X and logical Z are switched. But there are some Z stabilizer from the fact that we have to fix the 6 gauge qubit. So that kind of stabilizer is not preserved by the transversal H. So we will use the X error correction to map this stabilizer back, map it back to the coding space. So here is the circuit. So we will apply a transversal H here, and then apply a Z0 transversally on the encoded plus state, and perform a measurement and then X error correction. So they found that the universal quantum computation using only a transversal gate and error correction is possible, but it is not good, because when the physical noise approached the threshold, they found that the resource overhead increased rapidly. So there is another protocol that they suggest in their paper. The idea is quite similar. So here, we will have a Toffoli state here, and the Toffoli state can be used to simulate the control Z gate like this. And the control-C gate can be applied in this circuit transversely, where this is the encoded state from the triorthogonal code. And we perform X measurement here and decode and then apply H. And at the end, we will get a Toffoli state. So they found that this kind of circuit is good if you want to simulate a circuit which has a lot of Toffoli gates, because a Toffoli state can simulate Toffoli gates. But it might not good if we want to simulate another type of circuit that has like T gates or something like that. So to sum up, in this work, in this presentation, I explained that the magic state is an ancillary state which has two properties, universality and distillability. And we know that if we have an imperfect state, which input error rate is above the threshold, it's possible to distill to get a better ancillary state. And Brawi and Ha construct a protocol using the triorthogonal matrix. And in their protocol, the protocol consumes 3K plus 8 ancillary state of error rate P and produce K copies of ancillary state with error rate P squared. And Pasnik and Rickert show that the triorthogonal code, in the triorthogonal code, the transversal control-C is, control-C is transversal. And it's possible to construct a universal fault-tolerant quantum computation using only transversal gate and error correction. And these are my references. Thank you for your attention.
Sorry, could you go to one slide prior?
This one?
No, one forward. Yeah, that one.
Okay.
So you can increase the error rate from P to O of P squared using
Yes.
this procedure.
Yes.
Can you repeat this?
Yes.
Right? Okay,
Yes.
so you could do like a trial.
Yes.
Orthogonal.
So what I explained here is like a subroutine.
Okay.
Yeah. So we can use it recursively.
And it increases the error rate by 1 power of P each time, or does it double the power?
I think double.
Okay.
Yeah.
Oh, okay. Yeah.
So what's the overhead that comes out of that? If you iterate, what's the overall effect on the overhead, the number of qubits, physical qubits you need to get one?
I think it will grow exponentially.
With what?
With the number of iteration.
Okay, and so what does that mean if you want to get an error rate of epsilon? How many qubits do you need?
Maybe log?
It's a polynomial log.
Yeah, polynomial log. Yeah.
Okay. Any other questions?
Maybe I can ask a very quick question. So there are two approaches, like magic state distillation. So maybe you can compare.
Oh, so because they simulate, they distill the different types of magic state, and they have a advantage and disadvantage. So let's say here they will here in the protocol they will produce an ancillary state A. We know that the state A can be used to simulate the Toffoli gate. But if we use the another protocol that directly produce the Toffoli state, which can simulate the Toffoli gate, in that protocol we can save a lot of number of overheads. But if we want to use the protocol to distill the Toffoli state, and we want to simulate the circuit that has T gates, so it will not be efficient in that way.
Okay, thanks.
Thank you.
Here we begin. So, hello everyone. I'll be talking about quantum LAPC codes. So let me say a little bit about the story behind it and the motivation for defining quantum LDPC codes. So Shannon, in his famous paper, introduced a couple of notions, including channel capacity. So he proved that reliable transmission of information above the channel capacity with rate about channel capacity is not possible. And also he showed that there exists codes with rates that are arbitrarily close to channel capacity and which have vanishing error as the block length increases. But the problem is that his proof is based on probabilistic arguments and it's not constructive. So, but in fact, implicitly, his proof shows that random codes are capacity approaching. But still, it's not going to be useful because in order to be able to use codes, we need to be able to do the encoding and decoding efficiently. So that led to introduction of linear codes, where the code is basically a linear subspace, and instead of having to so for encoding, instead of dealing with an exponential size code book, we instead have just, we can specify it by a polynomial size basis. So that solves the problem of encoding. And in fact, the same argument shows that random linear codes are capacity approaching. But what about the efficiency of decoding? So as was explained in the earlier talk, the maximum likelihood decoding is NP hard for general linear codes. So the solution that people considered was to focus on subclasses of linear codes instead. And instead of aiming for sort of optimal decoding probability, we aim for suboptimal decoding. And so low density parity check codes, or LDPC codes, are a subclass of linear codes with sparse parity check matrices. And they satisfy these nice properties that we want. So they are capacity approaching and they have efficient encoding and decoding. So the same sort of motivations hold in the quantum setting. But in fact, it's having fast decoding is even more important in the quantum setting because quantum computation is likely to require active stabilization, and longer decoding means longer active stabilization and higher cost. And on the other hand, if the errors accumulate faster than we can detect the errors, then it's basically impossible to do quantum computation. So it's very important in the quantum setting, and there is another advantage of having quantum LDPC codes. And that's because, so when we have a low density parity check matrix, that means that when we want to basically find the errors, find the error syndrome, we just need to interact a small number of qubits. So that's another advantage. So in this presentation, I'm going to focus on CSS codes, CSS quantum LDPC codes, which are basically CSS codes defined by a pair of codes CX and CZ, where CX and CZ are classical LDPC codes. Okay, so let me quickly go over a little bit of history on the topic. So classical LDPC codes were introduced by Gallagher in his PhD thesis in 1962, and it was overlooked for a long time. So something like 30 years later, people started getting back to working on it. And there has been a lot of constructions with different properties and different type of constructions. And most of them are basically based on random constructions. And so I won't be able to talk about the details of that. So let's move on to the quantum case. So in the quantum case, as I said, so in a CSS quantum LDPC code, we have CX and CZ, which are classical LDPC codes. So if they're easy to construct, then why is it difficult to do it in the quantum case? It turns out that the constraint that CZ perp should be contained in CX basically makes it very difficult to come up with, good constructions. And so the random constructions don't work anymore. And so the first quantum LDPC codes were introduced in early 2000s, and since then there have been several constructions that have been introduced, but most of them have this problem that they either have vanishing rate, or if the rate is not vanishing, they have bounded minimum distance, and that's not something that we aim for initially, because we are hoping to get something like linear minimum distance similar to the classical case. And there is another motivation which comes from a result by Daniel, which states that good quantum LDPC codes with sufficiently large growing minimum distance and basically non-zero rate can be used to achieve fault-tolerant quantum computation with asymptotic constant overhead. So there are actually three constructions which are surface code constructions that have non-vanishing rate and minimum distance that is actually growing with the block length. So one of them is basically logarithmic, and it's based on a construction based on Cayley graphs. Another one is something like n to the alpha for some constant alpha, which is, I guess, bounded by a constant like 0.3 or something. And the best known result, sort of the state of the result, is a construction due to tillage et al. That is, has non-zero rate, and the minimum distance is proportional to the root of the block length. So in the rest of the talk, I'll be focusing on that construction. So before that, I need to give you two definitions. The first one is the Tanner graph, which is sort of a graphical representation of linear code. So let me explain it here. I guess it will be more clear. So suppose that we have some parity check matrix that looks like this. Then corresponding to each row, we have a check node, and corresponding to each column, we have a vertex, which is called a variable node. And the Tanner graph is a bipartite graph, which is looks like this. And CI is connected to Vj if and only if the corresponding element is 1. So C1 is connected to V1 and V3, and C2 is connected to V1, V2, and V4. So this is our Tanner graph corresponding to this parity check matrix. And this is actually useful for decoding purposes, and I won't be able to get into that, but it's quite useful. The next thing I need to describe is the graph product. So consider two graphs, G1 and G2, with vertex and edge sets V1, E1, and V2, E2. Then the product of the two graphs is defined as the graph which has vertex set, which is the product of the vertex sets. And the edge set contains, so xy, and x prime, y prime are adjacent if and only if the first coordinates, either the first coordinates are the same and the y prime is an edge of G2, or y is equal to y prime, and x prime is an edge of G1. So let me give you an example of that. So suppose that G1 is a path of length 3, and similarly G2 is a path of length 3. Then corresponding to each pair, we have a vertex. So the vertices in each row have the same first coordinate. So they're adjacent if and only if the corresponding nodes are adjacent in the graph G2. So it's something like this. And we have a similar thing for the columns. And so if we had started with like a cycle, then it would be something like this. And these are basically connected. And it will be a tiling of a torus, similar to what we have seen in the toric code. Okay. And note that for any pair of edges AB and XY in G1 and G2, we have a 4 cycle. So these two vertices are adjacent because they have the same second index, and the AB is an edge of G1, and similarly for the rest of them. And this is the main property that is used in the construction, as we will see. Okay, so let me quickly recap the toric code. So it's defined on a graph of this form, an L by L lattice. And it's a CSS code where HX is the vertex edge incidence matrix of this graph, and HZ is the face edge incidence matrix. And recall that in this case, the number of qubits is, or the block length is 2L squared. And the number of logical qubits is 1, so the dimension is 1, and the minimum distance is L, which is proportional to the square root of the block length. Now, the construction that we want to consider today is basically a generalization of the toric code. That's why I have chosen this one, and also that's because it's the sort of the state-of-the-art result. So it has the same property that the minimum distance is proportional to root n, but in contrast to the toric code where the rate is 0, it has a constant rate. So it's quite a good generalization of this class of codes. So we start by looking at the Tanner graph corresponding to HX. It looks like something like that, where we have variable nodes and check nodes. And similarly, we can define HZ. It looks quite similar to this, but it's defined in the dual lattice. And if we put them together on the same graph, we get something like this. Then in this new sort of graph, we can see that this is basically a product of two L cycles, similar to what we saw here. Okay? So this sort of, and from this representation of the toric code, it can be seen that HX and HZ, in fact, define a CSS code. And so that's basically because of the property of the product structure of the graph. So that sort of motivates generalizing this idea. So we start with two Tanner graphs, G1 and G2. Then we consider the product of the two graphs, which has, remember that the edge set is the product of the vertex set is the product of the vertex sets. So we will have V1 cross V2, V1 cross C2, and C1 cross V2, C1 cross C2. So these are the 4 subsets of the vertices. And then if we look at the subgraph, which is induced by these 3 subsets of the vertices, we can think of it as a Tanner graph corresponding to some linear code. we call it Cx. And similarly for this one and these two, the induced graph, we call it, it corresponds to some code Cz. And now the claim is that the pair Cx and Cz define a CSS code. Okay? So let's see a quick proof of that. So in order to show that, we just need to show Cx perp is contained in Cz, and that's equivalent to showing that the rows of Hx are orthogonal to rows of Hz. Now, remember that the rows of Hx, so if we look at a check vertex of the corresponding Tanner graph, say C1, V2, then the row corresponding to that is basically the characteristic vector of the neighbors, the vertices that are neighbors of that vertex. And similarly for a vertex in V1 cross C2, which corresponds to a row of HZ, the row corresponds to the characteristic vector of the neighbors of that vertex. Now, the inner product of the two rows is equal to 0 if and only if the nodes which are sort of adjacent to both of these two vertices are, the set has an even size. Okay? Now, it's not difficult to see that that's the case. So if a vertex in C1 cross C2 wants to be a neighbor of both of these two vertices, then the only vertex that can be adjacent to it is the node C1, C2. And similarly for V1 cross V2, the only vertex that can be a neighbor of both of them is V1, V2, because they need to have the same coordinates. So now, so the size of the neighborhood is at most 2. And it's easy to see that if there are two cases, if V1 is not adjacent to C1 or V2 is not adjacent to C2, then the neighbor set is empty. And if that's not the case, so V1, C1 and V2, C2 are edges in G1 and G2, then the neighbor set is exactly this set. And so it's the 4 cycle that I talked about earlier.
Almost time.
Okay. Now, okay, so that's all I wanted to say about the proof. Now, I will just mention the results about the dimension and the minimum distance of the code. So we can define the transpose of a Tanner graph as the Tanner graph which is obtained by just removing switching the role of the variable nodes and the check nodes. And we obtain, so that the new Tanner graph corresponds to a new code, and that code is called the transpose code of the original code. Now, the result that I'm going to talk about next is basically they show that the minimum distance of the code is characterized by the minimum distance of the two original codes and the minimum distance of their transpose codes. And similarly, and the relation looks like this. The minimum distance is at least the minimum of D1, D2, D1 transpose, and D2 transpose. And also, the dimension is specified by the dimension of the original code and their transpose codes. And it looks like this. So K1 and K2 are the dimension of the original codes, and K1 transpose and K2 transpose are the dimensions of the transpose codes. And I guess that's all I wanted to say about the result. I won't be able to get into the proofs because I guess time is over.
So you said the Tor code was a special case of these codes. So what are the two graphs that you're taking the product of, the Tor code?
So in that case, there are cycles. They are basically cycles that I guess they correspond. So they're Tanner codes of repetition codes, I guess. Yeah. And so, yeah, it looks quite similar to this.
Any other questions? Okay, then next.